Okay, so on Tuesday we talked about hardwiring the decoding and control unit of the memory processor, and I showed you how any signal is generated, like T0, T1, T2, T3. Those are the signals that we need to generate control signal for them. And today I'm going to do one example for few instructions, and then uh, we good for this part of the class, and we will finish chapter 4 and move to the next chapter. Here we have a block diagram and architecture of Mario processor, which we discussed last Thursday. And I mentioned that we have read signals, write signals, and a bunch of other signals, plus timing signals. And in the top of this block diagram, I said that we have a control unit which generates needed signal, required signals to be applied to the registers. Okay, so and on Tuesday we already discussed one of those signals, but now I will go and start to build a control unit for few instructions. Okay, for few instructions, and you can just continue and complete this design. Okay, so what I'm going to do today, i'm going to design I'm going to design a control unit for few instructions. Which instructions? For three instructions. No matter which instructions we want to work on it, so we have 15 instructions, but let's just pick the first three instructions. So the first three instructions are load instruction, load X, it's store X, and it is add X instructions, which we want to design a control unit for these instructions. For first of all, for load instruction, we know that the opcode for load instruction is 0001. You don't need to memorize these numbers. Okay, so they will be given to you in the test. So if I ask you I'm not going to ask you what is the opcode of load instruction. It will be given in table, so don't worry about these numbers. So store instruction has the opcode of 0010. Add instruction has an opcode of 0011, and all of them of course have the address part as well, which is 12-bit address. And if we want to see which where are these bits stored in, we know that they are stored in IR. So these four four bits are stored in IR 15 to 12, and the address is stored in RR 11 to 0. But what we are interested in is the opcode part of the instructions, okay? Because the address is just the address. We want to design a control unit for these three instructions. The first thing we need to do is finding the writing the what's that? Writing the micro operations for these three instructions. Okay, let's do that. Load instruction, load instruction. Oh, first of all, before writing the micro instruction for any of those, we need that all of them have the same fetch cycles, okay? Same fetch cycles for all of them. So we say fetch cycle for all of them is same. So let's see what is the fetch cycle. We know that for fetch cycle, PC moves to MAR, memory content of MAR location moves to IR, and PC will be incremented by 1. Okay. Now that we reached to this point, we need to write the signals for these three instructions. First, for the first, second, third micro operations of this fetch cycle. For the first micro operations, we start at T0. The second one we start in T1. Third one we start at T2. Okay, we want to read from the PC. Okay, we want to read from the PC. What is the address of PC? If we go back and look at the address of PC, we know that the address of PC is 2. Address of PC is 2. What is the address of MAR? The address of MAR is 1. So let me write it in the form of binary numbers. It becomes easier. So PC is like 2, which is 0, 1, 0. MAR has the address of 1, which is 0, 0, 1. Memory has address of 0, which is 0, 0, 0. IR has address of 7, which is 1, 1, 1. And of course, PC has the address of, again, 0, 1, 0. Okay, that's it. We know that in order to read the data, in order to read from a device or from any component, we need to work with which signals. If you remember, we need to, because we have 6 signals, P5, P4, P3, P2, P1, P0. So for reading from any of these registers, we need to activate P2, P1, P0. In order to write to any of these elements, we need to activate P5, P4, P3. Okay, so these are the signals we need to activate. So let's move to the first instruction. The first micro instruction in the fetch cycle, a PC wants to move to MAR. So we want to read from the PC. When we want to read from the PC, we like map this address with P2, P1, P0. Okay, so which one should be activated? So P1. So if P1 is activated, we read from PC. We want to write to MAR. Let's map this address in the right cycle. So P3 should be activated. Okay, so T0, P1, P3 are the required signals in order to move a PC to MAR. So in our design here, if what was that? If P1, P3, P1 and P3 are activated in this design, the information of PC will be go on the bus and will be transferred to the MAR. Any question? Okay. Now that we reached to this point, let's move on and continue. For micro instruction number 2, we want to read from the memory and write it to IR. What is the address of memory? It's 000, so that's fine. None of those P0, P1, P2 should be activated because it's 000. We want to write to IR because we want to write to IR. What is the address of IR? Is 111. So P3, P4, P5, P4, P3 should be activated. P5, P4, P3 should be activated. And we need to activate one more signal. Can you tell me which signal should be activated for the second micro operation? Still, we need to, very good, M sub R. So we want to read from the memory. Okay, let's show it with capital R. So M sub R says that we want to read from the memory. Okay. So far, so good. Everything is fine. So we're happy with the phase, cycles. This what I'm doing here is exactly what you will redo for other instructions later. Okay. So listen carefully and learn. So number 3 is micro operation number 3 is increment in P program counter. And if you remember, I said that we have one signal control called increment PC, which if we activate this signal, then the value of the PC will be added by 1. Okay, do we need to add any read or write? No, of course we don't want to access to the data bus by the PC, so we don't need to go with any of these P's. Okay, so we don't need to activate any of those P signals because we already send the signal to the program counter just to increment by 1. Okay, so here I have a question. Do we need to reset the counter or no? Do we need to have CR here or no? I want to see some answers. One answer, I got one answer. 2 answers, 3 answers, very good. No, very good. I got 7, 8, 9, no. Why? Because we done with phase cycle. Okay, still we need to move to the decode and execute cycle. So we not done with the entire execution of the instruction. So we shouldn't have clear counter reset here. So far we did the first three cycles for the fetching an instruction, which is same for all these 3 instructions that we want to design a control panel, control unit for them. Okay, so let's just make sure that we keep all these micro operations in a safe place because we need them later. We need to go back to all of these micro operations later. And now we move to the the decode micro operation. Okay, so the first instruction we want to discuss is load instruction. Okay, load instruction. Load X. So what are the micro instructions of load? Okay, let's do that together. For load micro instructions in the decode and execution phase, we need to move IR11 to 0, which we usually call it X. Okay, we need to move X to MAR. Then we need to read the memory content of MAR location and move it to MBR. And finally, we need to put MBR in accumulator. Okay, now that we reached to this point, again, let's go ahead and write the micro, write the our signals for these three micro operations. The first thing we need to start from T3, T4, T5. Okay, so what is the address of IR? What was the address of IR? Can you tell me? The address of IR was 7. Oh, okay, 7. So address of IR is 7. What is address of MAR? Is 1. So it's 001. What is the address of memory? It's 000. What is the address of MPR? Is 3, which is 011, 011, and accumulator as the address of 4, which is 100. And if we write the micro instructions for, if we write the signals for this, the first thing we want to read from, IR. In order to read, we need to like set P2, P1, P0 signals. So we say P, P2, P1, P0 signals should be activated to read from IR. We want to write to MAR. MAR is P5, P4, P3, P5, P4, P3. So P3 also should be activated. What else do we need? That's it. Okay. So from the memory to MBR, in order to activate memory, because memory address is 0, that's fine. MBR is 011 because we want to write to MBR. 011 is P4, P3. So P4, P3. And because we want to read from the memory, we need to go with memory read. And finally, MBR wants to move to accumulator. We want to read from MBR. So we say P1, P0 should be activated to read. And we want to write to accumulator. P5 should be activated. Which other signals we need to activate it? Of course, we need to activate LALT because we want to read from MBR, not from the ALU. And the other signal should be activated is counter reset. So counter reset should be activated for the load for reset the signal. Any question for this part? No question? Okay, very good. So again, let's keep this information and move to the next instruction. Next instruction is after load we had store. Okay. Just give me a minute. Okay. Now we move to store instruction. For store instruction, store X. For store instruction, what we need to do, we need to put X to MAR, and then we need to read from IR to M. Oh, well, yeah, exactly. And then we need to move the accumulator to MBR, and then write the MBR to the memory location, which is defined by MAR. Okay, this one is like a store instruction. Okay, so as usual, IR has the address of 111, MAR has the address of 001, then MBR has the address of 011, accumulator has the address of 100, memory has the address of 000, and finally MBR has the address of 011. Okay, again here the question.
I can't see your screen anymore. I don't know if it's just me or.
No. I think my screen has been disconnected. Let me just, thank you for just letting me know about it. Just let me fix it. Can you see now?
Yeah, thanks.
Oh, okay, good. So this one is a store, like a store micro operations, and again we need to repeat the same thing. T3, T4, T5. Okay, we want to write from X to MAR. It's exactly same as like the load. It's exactly same. So the signals are same. So we can say T3, P2, P1, P0, P3. Like the orders no matter. So if you say P2, P1, P0, P3, or P3, P2, P1, P0, like it doesn't matter because there are just signals connected together. So it's not a sequential like signals. So no matter if you write them in like a different order. Okay, so I put all of you on mute. So if you have a question, just unmute your microphone and let me know. Okay, so what about the second micro operation, accumulator to MBR? So we want to read from accumulator, okay? So for read the data, always you need to remember this like signals. For read, we use P2, P1, P0, okay? So we need to read from accumulator, which has the address of 3. So P2 will be 1, and we want to by the way, that's fine. And we want to write to MBR. MBR is P5, P4, P3. So we say P4, P5, P4, P3. And because MBR is reading the data from accumulator, not from the ALU, okay, because it's reading from the accumulator, it's reading the data from accumulator, not data bus. We set ALT to 1, okay? So set ALT to 1. So every time MBR read from data bus, LALT is 0, so we don't need to set it. If MBR read from accumulator, LALT should be equal to 1. Okay, so this one is a rule. So this one is a rule. Every time MBR wants to read from the data bus, we don't need to set LALT. Every time MBR wants to read from accumulator, we need to set a LALT to 1. Any question for this part? So LALT works for both MBR and AC. Okay, so for both of them. Okay, so let me just go back to our let's go back to our signals, and we're done with this part. And let me just open the chat box to make sure that no one is asking questions. Okay, so now the next micro operation, the last one, MBR will be like moved to a memory. So we want to read from MBR. So it is P1, P0, which reads from MBR. It wants to write to the memory which has address of 0. That's fine. No P4, P5, P3 because it's 0, 0, 0. And we want to write to the memory. So we should active MW. And the last control signal we should activate is counter reset. Counter reset should be activated in order to reset the counter. So this one is for restore instruction. Any question? Okay, so now that we don't have any question for this part, let's move to the last instruction. So let's put it in the box because we need it later. Okay, so far, let's go back and do a review from the beginning. So far, we have the fetch cycles for all instructions 1, 2, 3, and we have decode and execution cycle for load, which is I'm still waiting for my screen to get loaded. So still wait. Okay. Just it has like a delay, like 10 seconds delay. Okay, so this one is the load execution and decode, and also we have store decode and execution. And the last one is like for add. The last instruction we will learn today is add. Of course, the other instructions are almost same. So we go with add X. What does add X do? Add X gets the data from address X and add it to accumulator and place it in accumulator. So what are the micro instructions? Again, the same thing. MAR moves X moves to MAR, then memory address moves to MBR, and accumulator and MBR will be added, and the result moves to accumulator. Okay, so we need to write the timing for these 3 micro instructions. So again, T3, T4, T5. The first one is exactly the same as the previous one, is P2, P1, P0, P3. The second micro operation is same as the second micro instruction for load instruction. So it is P4, P3, MR. Okay, and the last one, we want to add 2 numbers and put it in the accumulator. So if now we should look to accumulator signals. Accumulator has some like control signals which consist of A0 and A1, and it determines that what does the accumulator do. So accumulator can add information or subtract the information based on these signals. So we need to activate those signals. If we look to the ALU control, we see that for adding the signals, we the only thing we need to do is like setting A0 to 1, setting A0 to 1. And because we want to write to accumulator, the address of accumulator is 100. So we need to activate for writing the signal, we need to activate P5 signal. By the way, because this data moves directly from MBR, we don't need to include it. So we because the accumulator is not reading the data from it's not reading the data from what's that from the bus. It's reading the data directly from the MBR and AC through the internal connections. Okay, so let's see what other signals do we need. Let's think about it. Of course, because we need to of course we need to because we want to write to the accumulator, we need to activate accumulator. Yeah, we do need to activate accumulator. So we should go to P5 because P5 lets the accumulator write the data. And of course we need one more signal, which is LALT, which tells the accumulator to get the data from MBR, not bus. And finally, we need to reset the counter. Okay, these are the signals we need for these like micro operations. Let me just explain one more time. T5 is T5, okay, so no question for that. A0 tells the accumulator to add 2 inputs. P5 tells the accumulator to write the data after doing the arithmetic calculations. LALT tells the accumulator to get the input from MBR, not data bus. And CR tells the processor that this instruction is done, so reset the counter. Okay. Now that we reached to this point, let's again put them in a box. Okay. Now we have, let's zoom out. Now we have all 2 instructions and their signals, and of course the fetch cycle. And now it's time to build our control unit. Okay, so let's see how we can build the control unit. Okay. Okay, so here is, can you hear me? Just confirm.
Yeah.
Okay, good. So here is the opcode part of the the instructions, is opcode, which is IR 15, 14, 13, 12. Okay, these signals comes out, and here is Let me just let me use my ruler to draw the lines. Okay. 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 Mm-hmm. And we move to the last piece. It's here. And it's here. Okay. So here we invert like those signals. Okay. Now we have 4 opcodes, and we want to build the signals for load, store, and add. Let's have three different AND gates. So the first AND gate is here. Make it smaller. The second AND gate is here. And third AND gate is here. Okay, let's give them names. So this one, the first one is load, for load. The second one is for store. The third one is for add. Okay, so the load has the opcode of, what was the opcode of load? Let's take a look. The opcode of load was, let me just, what happened? Why it's blue? Oh, because it's very, oh, I got it. The opcode for load is 0001. 0001. So we get 0001 from these signals. So 0, 0, 0, 1. So this one is for load signal. So if the opcode is 1, this signal will be on. For restore, we should go with 0010. So 0, we get the 0 from here, 0, 0, 1, 0. So 1 comes from here, 1, and 0 comes from here. This one is for store signal. So if a store signal is activated, if the opcode is 0010, the output of this gate will be on, will be 1. What is the light opcode for add is 0011. Let's do that. 0011. So 0, 0, 1, 1. 1 comes from here. And the other one comes from here. Okay, so if this signal is activated, like if the opcode is 0011, this add signal, this add gate will be activated and the output will be 1. Any questions so far? Okay, now that we reached to this point, it's time to move on for each individual signal. The first thing I want to do is like drawing 6, 7, 8, 9, 10, 11 vertical lines. 11 vertical lines, okay? So these 11 vertical lines are here. So let's do that. Let me see if I can use my, okay, 11, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. In fact, we need 12. 12. 12 signals are here. What are these signals? Let's just label them. These signals are P0, P1, P2, P3, P4, P5, A0, A1, counter reset, counter reset, we need memory read, we need memory write, we need ALT, and we need one more. We missed one signal, so we need one more, and this signal is, what is this signal? Of course, this signal is increment PC. Okay, so we have these signals. What are these signals? These signals are the signals that are coming from this control unit and connected to the other elements of the circuit. So what we are designing now, we're designing this control unit and those signals coming out from this control unit, okay? So, now that we reached to this point, we need to have some other signals vertically, okay? So let's just build 6 vertical lines. Let me change the color. 1, 2, 3, 4, 5, 6. Let's go with 7, 8, no matter, just bunch of them. Okay, so 7 is fine. So be careful. These signals here, these wires here are not connected to each other. if they were supposed to be connected, I would use like a dot, like this, to show that those two vertical and horizontal lines are connected to each other. So here, none of them are connected. And what, let's label these signals. What are these signals? These signals are, in fact, T0, T1, T2, T3, T4, T5, T6, and so on. So these are the signals. Now, let's move. Let's move on and see what else we need to do. So let's go ahead and write the first fetch instruction. The fetch instruction, okay, the fetch instruction is not related to the opcode section. The fetch instruction will be executed every time that we want to execute a new instruction. So we don't need to like check the opcode for the fetch instruction. So what do I say? I say if, here is important, if T0 is active, T0 is active, just I use different colors to like highlight the different signals. I would say if T0 is active, bunch of signals should be activated in order. Okay, bunch of the signals should be activated in order. So let's go up on our micro operations. So at T0, which signals should be like activated? P1 and P3. You see, if T0 is activated, P1 and P3 like are active. P1 and P3. So I connect this T0 to a buffer. It's not a NOT gate, just a buffer. And connect it to, what was those signals? What were those signals? P1, P3, P1, 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 P3, P1, P3, P1, P3. P1 connected to P1 and P3. In order to connect to P1 and P3, I'm not going to show it like this. I'm not going to do that. Instead of connecting to P1 and P3, I prefer to show it in this way. Let me just erase what we have here and I will show it. Okay. I would say it's like P1 and P3. So this one is P1 and P3. So we see that when signal the counter, this like the range counter, like counts from T0, T1, T2, T3, T5, T4, T5, T6. When it reaches like it starts from T0, when it starts from T0, these two signals will be activated. P1 and P3 will be activated. This P1 and P3 will be connected, will be connected to the devices here. What do they do based on these micro operations? If they are activated, PC like will be read and will be written in MAR. So by activating P1 and P3, we copy the value of PC on MAR. So the processor when gets like P1, P3, like this line will be executed. PC will be move to MAR. Is it clear? Any question? Okay, so let's go to T1. T1 say P3, P4, P5. 3, 4, 5. 3, 4, 5. Let me put it here. Okay. T1 is here. Oh, I'm sorry, I forgot the buffer. Let me just fix it. Just give me a minute. Okay. So here is a buffer and connected to T0. T1 comes here to buffer and goes here. It should be connected to P3, P4, P5. So P3, let's go all the way and just connect for those signals that we need, like this. Okay, so P3, P4, P5, P3, P4, P5. What other signal we need to connect? MR, memory read, memory read. So if T1 is like gets activated, the second micro operation of fetch cycle will be executed. The third one is here. Which signals should be activated for the third one? Let's take a look. Just increment PC. Okay, increment the PC. So these signals like are the fetch cycle of memory processor. Okay, now let's move to decoding section and execution section. Okay, I would say if we have T3, T3 is connected to like three different it's connected to three different gates. So the first gate is an AND gate here. Let's continue. I will explain why. The second one is here. And the third one is here. Okay. So this one is for load. This one is for store. This one is for add. Okay. So the other inputs of these three AND gates comes from here. So the load comes from here. The store comes from here. And add comes from here. First, let's focus on load. Okay, so I don't want to do all this three at the same time. So first, let's move it load. If we missed something. Something is wrong here. No one mentioned me. So this one, in fact, no. This one is connected to T2. Okay. Okay. Then T2 and T here is connected to T3. Okay. So the load instruction, if we have T3 activated here, T3 is activated, and the instruction is load. How do we know the instruction is load? From this opcode. What gonna happen? We will go to load instruction, and first micro operations of load will be executed. So load X first micro instruction says P3, P2, P1, P0 should be 1. So I say this entire virus P3, P2, P1, P0 should be activated. So this one sends the data, like the signals P0, P1, P2, P3 to the control path. Okay, what is the next instruction? Next, the micro operation. The next micro operation of the load is here. We should take care of this one. Let's do that. I say if signal T4 is activated, if signal T4 is activated and the opcode is load, the opcode is load, if T4 is activated and the opcode is load, we should activate P3, P4, and MR. P3, P4, MR. P3, P4, MR. P3, P4, and MR. So these signals will be activated, P3, P4, and MR. What about the last instruction of the load? It's T5, which comes from here. If the signal, if the timing is T5 and the opcode is load, which signals should be activated? Here, the last line, P0, P1, P0, P1, P5, P0, P1, P5, and LALT and clear counter reset. Okay, so far we got to this point. So this one is the complete control unit for load instruction. Let me put them in a, like some boxes so it becomes easier. So let me just highlight it. So this part highlighted in yellow is fetch cycle for all instructions. Fetch cycle for all instructions. This blue area is decode. It's decode execution for load instruction. Okay, and we need to continue it for all 15 instructions. The fetch instruction fortunately is same for all of them. So every time the counter reaches to 0, T0, this fetch cycle will be executed, but the other signals like need to be activated. So let's do the store instruction together. So store instruction, if we are in T3, I prefer to show it with different color. If no, blue is better. If T3 is activated and the signal is stored, so let's look to T3 store. So it's this one. Okay, here it says P3, P2, P1, P0 should be 1. So we say P0, P1, P2, P3 should be 1. Okay, so all of them are 1. Okay, now let's move to the next instruction, next time cycle, which is here. If T4 is activated, and the instruction is stored, so which signals should be sent to the control path? P234, P234, LAT, P234, P234, LAT. Okay, the last one, if signal T5 is activated and the instruction is a store instruction, which signals should be activated? So let's take a look. P0, P1, P0, P1, P0, P1, and what else? P0, P1, memory write and clear, memory write and clear. Okay, so this green highlighted area connections is decode, execution, for store instruction, for store instruction. Finally, add instruction. If a T3 is 1 and the signal is add, which cycle should be activated, which signals? P0 up to P3. So P0, P1, P2, P3. That's it. If the signal is T4 and it is add instruction, P3, P4, MR, P3, P4, MR, P3, P4, MR. And finally, if T3 is T5 is activated and this opcode is coming from here. Do you remember? From here. And the opcode is 1. Which signals will be activated? A0, okay, A0, P5, P5, LALT and clear, ALT and clear. Okay, so this one, this light blue area is decode and execution field for add. Okay, so we done. We designed our control hardware. Okay, now we did a great job. We designed our circuit. So now this part, this what you see in all the screen is like a control unit which is able to generate control signals for the load, store, and add instructions. So we have 15 instructions. So we have 12 more instructions that I want you to be able to complete those instructions. Okay, so you are the like in charge of completing those instructions. So I will ask you, okay, just let's just design control signals for jump instruction. So you need to like complete this signals for jump instruction or skip condition or any other instruction. And now if you look to this design, if I build this circuit in the lab, if I build this circuit in the lab using the equipment and the gates we have, we already have a complete control unit for our circuit. And after that, if we like build this part, let me just, I'm waiting for my screen to be updated. Just wait a second. Okay, and in addition of that control part, control unit that we discussed, if we build this data path part with all registers, we have an actual processor, very good. So at the beginning of the semester, we even didn't know what is an AND gate, OR gate, but now at this moment, we can claim that we are able to design a microprocessor because we know how to design the data path and we know how to design the control unit. And if we design these like units and connect them together, we will have an actual processor. And what you are supposed to do as your final project, I will discuss in more detail later when I saw you. I will ask you to simulate or build these circuits with the simulator and show me the result. Okay, so here is the part we have. And by the way, if you remember in the block diagram of control unit, I said that we have like instruction decoder, which is here, and I said uh, we have. I'm just waiting for my screen to get updated. Okay, it's here, and we have input signals, which are these T signals, and we have output signals, which are shown here. Any question? Okay, so the next time I see you, you as an engineer, I expect that you be able to design an actual processor for me, not just simulate it. You can get to the lab and build the real processor because you know what are the fundamental and what are the basics of designing a microprocessor. Okay, so think about it, do some more research, try to complete this, try to extend these instructions with the fourth and fifth instruction. Just I'm showing here two instructions plus the fetch cycle. So try to add some more instructions and try to get familiar with logic simulator and try to simulate some of these parts of this circuits by logic sim. Okay, so we will discuss. It's not a homework. Just I'm telling that as do some practice. Okay, and we will discuss it in the next class in more detail. But I don't see any reason that if at the end of a semester, if you're not able to design an actual processor. Okay, so by the end of a semester, I'm expecting that all of you able to design an actual Maui processor because we go into all details line by line, step by step, and I'm explaining you how to design those parts. Any question? Okay, so that's enough for today. Let me stop my recording.